Swayam Prabha. Digital India. Educated India.
Just to reiterate what I have said in the last couple of sentences, is that this Cartesian coordinates and so on, so there is no problem. But however, if the coordinates involve some angle measurement, then the addition, treating them as vectors, will be a problem if the angle is finite rotation. But however, we said that we took this example in detail. Because this is important for us, either now or later, we are going to have some angular motion. So how we treat the angular motions is of utmost importance. So here, let us say there is a point P here, and this is OP is the position vector of point P, and then we are subjecting this point P to a rotation about an axis N and a small angle theta, but let us just say delta theta. So anyway, we have seen this, so this is only recapitulation. So we said that this OP will become OP prime, R will become R delta R, and PP prime delta R, and OP prime is the new position vector once it undergoes an angle of delta theta rotation. So we went through a lot of detailed derivation and all that was there in the last class, and essentially what we require, PP prime, is a change in the position vector R for a rotation of delta theta, and then here we wrote delta theta and cross R, right? So this is what we have derived, because if it is this delta theta is finite, we have so many sine and cosine terms, and then all those cosine terms got cancelled with 1, and then sine terms became delta theta, and finally it follows the vector addition. So this is what we have done. So this is a very important one. And then if you derive, if you take a quotient with time, so dividing by time, by delta t, then we get delta r by delta t. So here, so this delta r by delta t will become the velocity, and this becomes angular velocity and cross r. Another simplification which we have here is that this omega n we represent by a vector omega. And so that means that this n delta theta, instead of that, we call this as a vector omega, whose magnitude is omega and direction is n. So the same direction is also going to represent the omega vector, whose magnitude is omega, and you can also say n. So if that is there, either you can write it in this manner, okay, with delta t, or we can even write it either omega or even theta dot as a vector. So all these things are very important for us, okay, omega cross r. So this is a very important result for us. So that means that any position vector r here, OP, if it is point P, if it is rotated about a vector n with an angular velocity of omega, so then the P will have a velocity in the direction PP, we can see it there, and which is given by omega cross r or theta dot, which is a velocity, angular velocity vector and times r. Okay, so this is one important rotation aspect of our kinematics. Then there is another important aspect, is the transformation. Transformation of coordinates. So essentially, now we have Cartesian coordinates. So many times we like to use other coordinates, and we should know how to switch from one coordinate system to another coordinate system in a seamless manner. So one of the, just in 2D, if you just see 2D, I'm going to go for 3D very soon. So in 2D, we have polar coordinates. So we have xy and point P here. So here, this point P, which is having a coordinate of r theta in polar, so we can convert it, x is equal to r cos theta and y is equal to r sin theta. So this is going from, given r theta, you can get xy, or given xy, we can also have, very simple, okay. So this is the going from one coordinate r theta to x or x to r theta. So that's one of it, but we need how the unit vectors change, transform. So that means that we have I and j here, and here this we call as ER and E theta. So where this is theta. And if you want, we can even write I and j here. The directions are the ones which are important for us. So whether they are here or here, it doesn't matter. So the I and j are like this, and ER, E theta are subtending an angle of theta with fundamental ij. So we need a relationship between the fundamental reference axis here and fundamental reference axis. Either you can write it in, for example, you can write So we can, I just put a dash here, which I need to fill up. Okay. So ER, if you want to get so if you want to get ER, then it is I cos theta plus j sin theta. So we can even say that cos theta and cos theta. So because this is totally I, cos theta times I and sin theta times j. So that will give you ER. So similarly here, so we can do the other. So actually it is minus sin theta and here cos theta. So this is written in the matrix form. So we can write it in this form, and this is called the transformation matrix. Sometimes we call it as A. Right? So sometimes we call it as A, the transformation matrix from Ij to ER E theta fundamentally. And we can also see Ij's also can be, so similarly Ij can also be written in terms of ER E theta. That's also is possible. So in which case it will become cos theta minus sin theta here and sin theta so this is the transformation matrix in the opposite, in the reverse sense. And you can see one interesting thing here is that this is nothing but the above A of transpose. So in fact, these terms here, A here, these terms A, if you call this A, so ALM, you can see that this is A11, A22, and A21, A22 is nothing but cosine of the angle of, let us say, how do I call it? Actually, it's more general, 1x2. It's more general like this, x1 prime, x2 prime. And if you write x1 prime, x2 prime, from unprimed coordinate system to prime coordinate system. So here we call it IJERE theta, or in general it can also be written as x1, x2. So what A means, ALM is nothing but cosine of the angle XL prime and XL. So this is how it is. So that means that this is cosine of the angle between XL prime coordinate, the new coordinate system, to the old coordinate M. For example, if you want here, this A11 is nothing but the cosine of the angle between ER and I. So that's cosine theta. And similarly, ER and J, cosine of 90 minus theta, that becomes sin theta. So this is how the generally transformation matrices. Another, of course, is fundamental property of this transformation matrices is that these are orthogonal transformations. So the A transpose is nothing but A inverse. So that means that A and A transpose are related by inverse relationship. Okay. So this is how this can be done in this simple manner, if this is simple. So having understood this, so how can we derive the relationship in general? In general, for example, in this polar coordinate, so how do I get the relationship in velocities? Okay, so the position vector r here, for example, is given as r times er, right? So then I want to derive the velocity relationship here. So this is r, and well, you can call it as r. The magnitude is r, and it's in the direction of er. So now if I want to get the velocity here, dr by dt is the differentiation of this in with time. There are two terms here as a product. So it's dr by dt times er and r times der by dt. Understand? So there are two terms. So this is nothing but r dot, and this is r times der by dt. What is that? So er is not constant with time, because with time the theta is going to change. Theta may be a function of time, and then theta is going to change. So once the theta changes, so that means that the er is going to change. Er, for example, as it goes, so then this becomes er prime, and this is der prime, right? As it increases. So how do we get this time derivative of er? Er is going to occupy a new position, er prime, and it's going to change by a small angle delta theta. And we know that whenever that result which we have derived can be applied here also, right? We have generalized, for example, for r, we said that dr by dt under rotation is simply omega cross r, or for that matter, we can even say theta dot r, or we can even say whatever theta n. So all these things are equivalent, right? So that means that here I want to get, instead of r, I have er, der by dt. So what is der by dt? So in the place of r here, this is the general rule, right? So I want to get ddt of er. So that will be nothing but theta dot n times r. Okay. So what is the angular rotation here? So if this point P is moving, so r may increase. That's the translational part. But the rotational part is because of theta. So when theta is changing, when it's going to have a time derivative, when it's going to have an angular velocity, so it is going to affect here, right? It's going to affect here because it is going to cause a change in the direction of er, so which is going to cause delta er. So that is nothing but going to contribute to ddt of er. So can you tell me what is this one here? So I will write der by dt. So we have done it in some other sense. Okay, we just took, in fact, last time we did. So we did. Last time we did, if er changes to er prime, this is delta er. And then if you want to, the magnitude of this one is nothing but delta theta times 1. And then if you take a time derivative, it becomes theta dot. And its direction is e theta. That's what we said. That's exactly what I'm trying to get here also. So you should be conversant with this procedure. So here dr by dt is nothing but omega cross er. So what is omega here? Omega is theta dot, of course. And what is the direction here? So the angular velocity, so in these two dimensions, if you are going to have an angular motion, so how is it? Theta is changing here. So the angular velocity here will be in this direction. If theta is having a counterclockwise moment, then in the form of a vector, the angular velocity vector can be shown in this direction, which is perpendicular to the board, and it is k. So we can write it as theta dot k, and we have er. So these are two vectors. So k times k cross er. So we have a k here, and then we have to take a cross product with, so there's a k here, we have to take a cross product, remove these things, necessary things. So here k, theta dot k, and if you take rotate it in a right hand screw, then it will be moving in the direction of e theta. So this k cross er is nothing but theta dot e theta. Understand? So that is the important part. D dt of er is nothing but theta dot e theta. So here, so in this place now I put, understand? So this is a very slowly going from in the polar coordinates, we can understand these things. So velocity is nothing but then, if you express it in terms of polar coordinates, so this is how it is going to be expressed. So it's r dot er plus r theta dot e theta. So this, for example, we didn't do that for er. Of course, er is going to change. Okay, I'm sorry. So now if you go for acceleration, one more step. So we can do it quickly now. Now we understand. So if you want to go for acceleration here, dv by dt, so we have to differentiate each one of them. So this is a product of two. So it is r double dot er and r dot, what is er? Der by dt. So change in the er is due to that theta dot. So just like we have done there, so this der by dt, maybe I'll just write it here, one more step, and here space here. So it is r theta dot d. Okay, so these are the terms that are involved in with time derivative. So you can see now here, the r double dot er, and this is der by dt, which we have done just now, is nothing but theta dot e theta, and this is r dot e theta. So these are as such. So what is the last term here? R theta dot. What is dz by dt? So again here, it is nothing but it is theta dot k times e theta. Okay. So e theta is here and theta dot k is in this direction. So if you take a cross product k cross e theta, so then what happens is that a right hand screw rule moves perpendicular to this, but in this direction, which is minus er. Okay, so it is theta dot minus e theta. Right? So that is this part, theta dot minus e theta. So if you combine all these things, it's very simple. So it is r double dot minus r theta dot square er, and r theta double dot. There are two terms, r dot theta dot. Okay, so this is another way of looking it in a very elegantly. So once you are used to this way of treating these vectors, so it really falls in place, right? So the most important thing which we have made use here is this one. So whenever there is a rotation that's involved, then the change in that r here, r d dt of that is nothing but theta dot n. So that is nothing but the angular velocity, and this is the direction, and then the r. So you have to take a cross product appropriate. Okay, so this is how we do using our knowledge of this angular velocity as a vector. Okay, so this is the polar coordinates. So there are two things which I have introduced just now, is that this part d dt of r is theta dot r. Another thing is the transformation of coordinate system of coordinates. Okay, so now let's continue this one to a more complex problem. The polar coordinates, cylindrical coordinates is nothing but an addition of one more term, zk. So zk is not going to offer you any complexity. Another plus zk, you have to put it here. Okay, plus zk, a third direction. And if you want to take a derivative, it is z dot k. K doesn't have any time derivative, it's constant. And then if you one more derivative, it just becomes z double dot k, nothing more than that. So cylindrical coordinates is no more different from polar coordinates. But spherical coordinates are really going to be a little clumsy, but we need to do it. Then only we have a hold of all these, the transformations and expression of velocities and so on. Now let's look at spherical coordinates, and it's a little bit exercise for you in 3 dimensions. So the spherical coordinates, how we express the position vector and how we derive velocities and acceleration. So last time I think I told you how to give that. I showed you a slide also. Okay, so the spherical coordinates here are given by the r, theta, and phi. So r is the distance from origin to the point P, This is the vector, position vector, but anyway, so r is the distance r, and its projection here given by p prime on the xy plane. And if you join that OP prime, so this is the angle phi, and from the vertical axis z, so the angle to this OP is given by theta. So this is one way of doing it. This is on the other hand, there is also another thing where they say that this is theta and this is phi. So theta and phi sometimes, I think, may follow. This is the one which is most followed, but then some people follow this as theta and this as phi. So phi is elevation. So they put it this as phi and this as theta. So in any case, so let's try to understand here. What are the basic coordinates here is r theta phi. So it's very easy to understand. So x is r sine theta cos phi, and y is r sine theta and phi. Z is theta. So this is from r theta phi to xyz coordinates. Okay, and then reverse also you can put it. So for example, r is nothing but and this theta is nothing but this is x square plus phi square. Last time I think I did this. I'm sorry. Okay, so this also I wrote it last time. Now I want to move further. So trying to get the relationship between ijk and ijk are easy to understand. So ijk are nothing but these things. This is I, j, and k. And now what we would like to do is that we would like to get the unit vectors in r theta phi coordinate. So how we get this er, e theta, e phi? Okay. So these are the unit vectors, vector coordinates. So that's nothing but increasing r gives you the direction er, right? And increasing theta gives you e theta. So everything else is kept constant. So phi is kept constant, r is kept constant. So theta is increased. So that means that this is e theta. So there is a circle drawn on P in the vertical plane. So this is a vertical plane, right? Because this angle theta is measured in the vertical plane with including z and r. And then we have with r theta constant, phi is increased. So for example, phi is increased like this. So this is e phi here, or here we have this is e phi. So e phi is in the direction of increasing phi, keeping this p. So that means that you are going so if you draw a circle in a horizontal plane going to the P, and then if you draw a tangent there, so that becomes E P. Okay. So these are the E theta, ER, E theta, E phi. So it's important for us, for example, the position vector R to start with. So position vector R is represented by This is the starting point which we need to do. So this is the position vector. So the position vector here is given in this form. So if you want to do a time derivative of this one, so V is what? So it's R dot ER and R TER by. So this is the interesting point here. I can proceed further. Interestingly, what is this? The dER by dt. What is the change in the ER because of the change in the coordinates? So the changing the R will not affect the direction of ER. But however, changing the theta and phi, so the ER, for example, if you increase theta, so it's going to bend down a little bit. So that means that it's going to have delta ER. So similarly, if you change the angle phi, then P is going to move along this circle and then its angle is going to change. Phi is also going to, ER is going to change its angle. Okay. So it's going to, so this time derivative of ER will be affected by change in theta dot and change in phi dot. So theta dot, you can take it to be an angular velocity vector. So what is its direction? Can you tell me? What is, for example, theta dot? So d dt of ER is due to change in theta and P, or due to, we can say, theta dot, and so it's affected by both. So if there is a theta dot here, so can you give me what is the, if it is only pure theta dot? So that means that if it's going to increase theta here, so what is it's going to be represented as an angular velocity vector? So if it is angular velocity vector, so what is it's going to be? So if theta is going to change, so that means that it is going in this direction. If so, then what is the perpendicular to it? Theta dot is the magnitude, but the direction here, if it is going to go in this vertical plane here through P, so then so if you look at this one with right hand system, so it is going to go in the direction of which direction? E phi. Going to go in the direction of E phi. So theta dot is really in the direction of E phi, not ER. Okay. And what about phi? If you have a phi dot, okay, its magnitude is phi dot. And what is going to, so phi is an angle measured in the horizontal plane here. And if it is going to rotate in the horizontal plane, so then it's going to have the direction k. So this is the angular velocity vector. So theta dot E phi and phi dot k. So that's what you're going to put here. So that means that V here, I have to put it as then so this is omega cross. Okay. So what is the problem here? So if this ER, E phi, they are pertaining to this, okay, triangle. So orthogonal axis. But then we have a K which is not belonging to ER, E theta, E phi. So that means that this K has to be converted to K in terms of ER, E theta, E phi. So I will just indicate it. We have to understand. Okay. So what we need is the relationship between the unit vector ijk, for example, to E theta, ER, E theta, E phi. So that's what because that's what we want to convert it. So for that we have we have, to start with, we have x is equal to, if you recall, so x is equal to r sine theta, right? R sine theta cos phi. And similarly y, r sine theta phi. So this, using this, we are going to have a relationship. So interestingly, as I said, that the transformation matrix can be obtained by looking at the angles. So now we are actually looking at the transformation matrix between the unit vectors. So unit vectors are what? Unit vectors are ijk or er e theta e phi. So these er e theta e phi are nothing but when a small changes in r, delta theta, delta phi takes place, right? So they are the change in p, the direction of p, while the r theta phi change by very, very minute infinitesimal quantities. So now that means that we need a relationship between infinitesimal quantities. For example, this one. So I'll put delta x differentials. So it's nothing but delta r sin theta cos phi and r sin theta. So I have r cos theta cos phi delta theta, right? And plus r, this one, r sin theta cos phi. So if I just do the differentiation, I have minus. So I have a sin phi delta phi. Okay, interestingly, this is the one where, so that means that this delta x is a representation of I, a small change in delta x. So this is, we can write it as I, and delta r is representation of er. And here, this is, now we have to write not in terms of delta theta, but either er or e theta or e phi. So we can very clearly see that if this is r and if there is a change in delta theta, so then this delta theta is nothing but in the direction of e theta. So that is r delta theta. So this is e theta. And similarly here, so this is e phi. So e phi is nothing but when a phi changes by delta phi. So this is the magnitude. So how much is that? So that is given by r sin theta delta phi. So this r sin theta delta phi is represented by e phi sin phi. Okay. So like this, we can have j, we can have k, right? So what I would write, so this is, I'm going to write it completely in a matrix form. So here, this is sin theta cos phi, sin theta sin phi, sorry, cos theta, cos theta, cos. And here minus sin. So like this, we have all of this. Also quickly, if I just write down, let me just finish it, just 2 minutes, sin theta sin phi cos theta sin phi. Hope you can see cos theta sin theta. Okay, so I'll wind it up here. So I gave the relationship between ER E theta E phi to ijk. So that means that k, if you want to convert to ER E theta E phi, you can use that last relationship and put it here. So omega k, you replace it by that and put it in this formula for v, and then you will get a relationship between the velocity in terms of r theta phi directly. Okay. Yeah, this is, please go through it. This is really a vector mechanics, and you should get a hold of all these things so that you will be able to deal with all these mechanics problems in any coordinate system. From one coordinate to another coordinate, you can easily go. Okay, I think I'll stop here.